thank you all for coming here. Thank you all for inviting us. So as Adam just said, I would like to talk a little bit about Hadoop at Spotify. Over the years, at Spotify we've been using Hadoop a lot. I'll tell you guys about that. And we're actually becoming one of the biggest Hadoop users in Europe right now, according to Cloud, which is kind of cool. But I'll tell you a little bit more about that. First, I guess it says hello Poland. This is Spotify, is that correct? So thank you, welcome. What I would like to talk today to you about is why do you use data at Spotify? What does it even mean? Why are we so concerned with data? Why do we work on a large scale? Why do we use Hadoop? I'll present a couple of use cases. I'll present you some statistics that we have. Give an infrastructural overview. Why do we use MapReduce in different languages? Talk a little bit about scheduling. How did we scale Hadoop? Because we've been using Hadoop for around about 4 years now. And what sort of lessons have we learned? How many of you do know what Spotify is? Okay, good. That's. I was a little concerned because we've launched it in Poland quite some time ago. Now, a couple months ago, I think.
You waited even longer, but we've been using it for years.
That's awesome. That's awesome. We never actually sort of try to mitigate that. Like people that use it, that's fine. But now it's for me, which makes me very happy. For those of you who don't know what Spotify is, very quickly, it used to be sort of iTunes in the cloud. You can stream music whenever, wherever you want, as long as obviously you have an internet connection. Although that's not completely true, we also have offline syncing. You can use it on your mobile device, you can use it on tablet, and we have desktop clients. And quite recently we released a web version. But I'll not talk about those kind of things. Because we're at a Hadoop meetup and we like data. So why is data important for us? Because we do music, we stream music, right? So what's the deal with data? And to illustrate why we use it, I would like to start with a small example, an analysis that we did quite some time ago. Nevertheless, pretty interesting. This is an analysis we did for listening behavior in Sweden, and we aggregated quite some data, and we sort of grouped it per weekday, and also per age group. So you see there we have in age group 0 to 17, although I'm not quite sure if we actually have users that are 0 or 1 years old, up until 60 to 150. Nevertheless, so we have different age groups, and we looked at their listening behavior. When do they use Spotify? Which moments of the day? And there are some interesting things that you can see here. Is that the green line? I don't know how is this even legible in the back?
No. Yes.
No. Yes.
The green line? No. Yeah.
There's a very small, like almost invisible green line here, and that's 0 to 17. And what you see, an interesting thing you see here is that there is a small dip from in the morning, and basically people start between 0 and 17 start listening a little later to Spotify, which probably is that they go to school and don't listen to Spotify. But during the rest of the day, their usage is significantly higher, except for in the weekends. This is actually Friday, Saturday, and Sunday. And when we looked at this data, there were some interesting things to note. For example, here, I don't know, in the back it's probably not very visible, but there's a slight bump, and this is the night from Saturday to Sunday. There's a small bump here between, or in that night. Can anybody guess what that is? And the bump obviously means that there's increased listening going on.
Parties.
Yeah, it's after parties. So people go out, come home, this is around, starts at 1 in the night and then continues a little bit, only for a certain age group. So people between 60 and 150, I doubt if they go to after parties. I don't know. And another thing, what we realized, what we saw, is that a similar effect happens here on Wednesday to Thursday. Anybody can guess what that is? No? It's also after parties. In Sweden, there's this sort of phenomenon that they call Little Friday, Little Saturday, sorry. So also people listening to Spotify. Now we compare this listening behavior to Spain, and unfortunately I don't have the Polish stats yet. But if you look at how listening behavior is in Spain, it looks very different. So first, what we noticed in Sweden, we have the coloring of age groups is a little different though, but you don't see any of the age groups making a dip and starting later. So either kids between 0 and 17 don't go to school in Spain, or they just use Spotify. I don't know. Right, yeah. And this is actually over a longer period of time, so I doubt that. But nevertheless, another interesting thing is you see the same little bump here on Saturday to Sunday, but not on Wednesday. It's not very significant here. So Spanish people also do after parties, and I think it starts actually a little earlier. But most interesting is the behavior in the sort of midday, because you see that still 0 to 17-year-olds are far more high, like their usage is higher during the day. We see very significant dip in like older age groups. Can anybody guess what that is? Siestas, yes. We call this the Spotify siesta effect, where we see that drop. Yeah, for the rest, it gives you an overview or an idea of like how different listening behaviors are. Another thing that might be interesting is that we looked at what is the impact of Hurricane Sandy that was on the east coast of the US last October. This was the day that the hurricane hit the most, hit the hardest. And you see here, and I hope that you guys sort of see that this is sort of the shape of the US. California here, there are no people living here. That is true, there are not a lot of people living here. Florida and sort of the East Coast. Some clever colleague of mine, he actually puts geographical data into Excel and creates these heat maps. I thought I was coming right. Nevertheless, so you see Sandy, these colors represent how listening behavior is affected according to average listening behavior. So you see, especially here, and this is around Washington D.C., that there's a decreased listening, but sort of all this part where Sandy hits, you can see geographical effects quite good. Compare that to a day later, then you also see that this hurricane had moved up. So just like this before and then the day after, you see we can sort of track the weather. So then the question that I posed before, why data? For us, it's really to get more insights, and insights can mean on all sorts of aspects: business, operational. I'll talk a little bit about that more later. But data for us is very, very important. So then, another question is, why do we use Hadoop? Well, we have millions of active users on a daily basis. The last number that came out was that we currently have 26 million active users on a monthly basis. But those users together, they generate a whole lot of data. This data is way too much to put in a regular relational database and work with it. Or it's very expensive to buy a relational database system that supports that. Hadoop provides good value for money. It's open source, so no licensing costs and those kind of things involved. We can actually hack on it ourselves, so it provides good value for us. It runs on commodity hardware. You still need pretty beefy servers to, if you really want to do something with Hadoop, I think. It's not you pull out your old 486 from the basement and you run your Hadoop cluster on it. You still need a lot of memory, fast disks, preferably, to do something significantly with it. And it scales pretty well, as I hope all of you know. So just adding more capacities, or if you want to add more capacity, just add more nodes. So I want to go over a couple of use cases. How do we use data and Hadoop and Spotify? Which is main areas are reporting, business analytics, operational analytics, and we use it for in-client features. Back in the day when Spotify started, Spotify was founded in 2006 and our first launch was in 2008. And when we started building Spotify, we came to the conclusion that we will have, with the goals that we have set as a company, we will have a lot of users, which means a lot of data. But we had to provide this data in the form of reports to labels and licensors that have to pay artists. So Spotify's business model is we get income from ads, we get income from paying users, and for every stream basically that our users play, we pay an amount of money to the labels and they pay their artists or license holders, rights holders for music. And from the beginning, labels and licensors, but also advertisers and partners, they wanted data from us, and we knew that it was going to be a lot of data. So already back in 2008, some clever people at Spotify, they thought, okay, the relational database, that's not going to cut it. We really need a bigger system. So we went with Hadoop. And for us, reporting is really, really important because we basically need to keep a very good relationship with the labels. Without them, there would be no Spotify. But since we have a lot of data, Spotify started, a couple of years ago, Spotify was more gut-driven. I like to call it gut-driven. So decisions were based on a gut feeling. What do our competitors do? What do we think is an interesting feature for our users? But it wasn't really data-driven until our CEO said, guys, listen, we have so much data that we use for reporting. We collect so much stuff. Why don't we use it in the same way? Why don't we use data to test hypotheses and try to analyze it so that we can actually make sound and educated decisions? So what we started doing, we built back then a business intelligence team with analysts and with developers. They started working on analytics, mostly business analytics. And that still exists. Currently it's called analytics at Spotify, but the idea is still the same. We analyze growth, we analyze user behavior, we analyze sign-up funnels, so who comes in from where. You can sign up through your mobile, you can sign up through Facebook, you can sign up on our website, which medium works best, or which funnel works best, how do we optimize that, how do we test those kind of things. So those growth and the amount of active users that we have, those are very important key performance indicators of how are we doing as a company. And as I said, like for example, with those sign-up funnels, we can test that. We can provide different experiences to different groups of users. This is called A/B testing, where you create, you want to try out something new, and you deploy that for a bunch of users, a small group, and you test that against how does the feature perform when it's not there with the rest of the population. We do that all the time. So new sign-up, new features even in the client, new products that we launch, things like that. We've also started working on a Net Promoter Score analysis. Anybody familiar with Net Promoter Scores? Yeah. It's for those of you who don't know, it's basically you ask one question: how likely is it that you will recommend this product to a friend? We try to analyze that and get feedback on that, which helps us improve the product. We also quite recently done a segmentation analysis where we look at what kind of users do we have. You can basically divide our users into different groups. There are early adopters, there are people that are really like techie and into technology. You have mainstream listeners, and you have also people that sort of like wait until things become more mainstream, or people that simply don't care about new technology. So, like Grandpa, who's still doing his records, vinyl records, we're probably never going to get him. That doesn't really matter. But we try to sort of put people into different groups and try to optimize the product for different groups, but also for like what makes the most sense to do for the largest part of our after business analytics, we started doing operational metrics. So we collect also not only how our users behave and how what data our users generate, but also operational metrics like server stuff, disk usage, CPU usage, debug logs, and those kind of things. And by collecting all that data, we can do root cause analysis. We can do, for example, latency analysis. Spotify has historically been, we've been very proud of that. We've been sort of known for, even though it's an internet service, we don't buffer. It doesn't seem that we buffer a lot of data. We click and we play. So we want to constantly analyze like how is our latency doing. And we use it for better capacity planning as well. So we analyze a lot of stuff with our Hadoop cluster, but we also analyze our own Hadoop cluster with it, just to see how is our data usage growing, our data volume growing, how is our usage of the cluster growing, how many more users internal users do use Hadoop, things like that. So we can better plan for capacity expansion. Or people, how many more people do we think that we need in all sorts of different areas? How many bandwidth is consumed within our network? And about a year ago, I would say a year and a half ago, we started using data inside the client as well. We really promote that within Spotify to make features that are data-driven. Some examples are radio, that's very heavily based on what people play. We create top lists, for example, and we do recommendations. And it's interesting that we started doing recommendations initially we partnered up with some companies doing fingerprinting of audio. So like you have a classical track, for example, and you have another classical track and they have somewhat similar tempo, they have similar timbre, they have some attributes of the actual music are similar, and try to match those and say, okay, if this is a classical track, this might also be a classical track, and might be interesting for a user that played the first track. We initially deployed that in our radio feature actually, and but in parallel we started developing our own algorithms to do a similar thing, but not based on the audio data, but just looking at user behavior, user data. And it turned out that outperformed the whole music analysis, music fingerprinting algorithms. So we could do a better job with far more data than just simple, or not simple, very complex algorithms. And that was, I think that was for me at least, quite an interesting thing. By just throwing data at the problem. So I would like to share some geeky numbers with you all. Currently, we ingest about 600 gigabytes of compressed data for users every day. It's a compression rate of about 1 to 10 maybe. So that's 6 terabytes a day that we ingest. We ingest another 150 gigabytes of compressed data from other backend services. We have a lot of other backend services that have their own databases that we ingest. So, for example, we have a database containing all playlists of people. We have a database that contains all information, metadata about tracks and artists and albums. We ingest that as well. From that data, we generate about 4 terabytes of data every day in Hadoop. We currently have a 190 node cluster. But the order went out 2 weeks ago to expand that with 500 more nodes, so we'll be in, I guess, a month or two, hopefully we'll be at 690 nodes. Cloudera is helping us with that. They're consulting, and they said that this is probably the largest Hadoop cluster in Europe, a non-commercial Hadoop cluster. There are non-commercial government organizations that probably have better or like bigger clusters, but they can't tell us. And the complete cluster today is 4 petabytes big, but with that expansion we'll go up to 28 petabytes. We actually double the capacity per node as well. Let me talk a little bit about our data infrastructure. This is actually a picture taken in our data center. Our Hadoop nodes were taking so much power because they're basically running 24/7 and consuming all the power of the racks that we could not expand the racks any longer. So guys in the data center, where we have our Hadoop cluster, they have to go in and add more power to the racks, and that looks like this. Guys underneath floorboards. So how does our infrastructure look? It's not that complicated if you think about it. So what we have a lot of backend services. One of the backend services is where your client talks to your Spotify client when you play games, and we ingest that data into HDFS. We have a whole bunch of, as I just said, operational databases that are used for online systems, like playlists, like the metadata. There's a whole bunch of them. We ingest them. We dump databases into HDFS, either daily or hourly. And then we run MapReduce on our data. MapReduce is either done through MapReduce jobs. We call this pipelines. It's sort of an ETL process, which is done by Luigi, our in-house written scheduler. We recently open sourced that. Talk a little bit about that later. Luigi takes care of most of the MapReduce tasks. Next to that we have Hive, which is mostly used by analysts. So we don't use Hive inside our pipelines in our continuously running processes, but it's used for ad hoc queries into Hadoop. We've built a system on top of Hive that we call Spotify Data Warehouse, where like people can go in and create their own queries without having to know how to access servers or machines over SSH. Just a web interface where they can do all sorts of things, browse tables, save their queries, let it run in the background, get an email when their job has run, so that they can download it. And that data warehouse is also combined with our SQL databases that we have. We still use a lot of SQL databases, so they can also run that. A lot of aggregates that we produce go into our analytical databases. We mainly use PostgreSQL for databases for our DMS. And on top of that, we have dashboards, all sorts of funky graphs that people can build themselves. And they can write their own queries, they can create their graphs, they can hook them up. And yeah, that really is on the phone. Also output for things as I just told, reporting, stuff that goes to labels, and we use data in product features. So a lot of data is actually flowing back into backend systems, backend services. Radio, for example, they have the team that developed radio, they run their MapReduce jobs daily, and then the output of that is pushed back into their own service in all sorts of indices, whatever fits. Sometimes it's Cassandra, a service that uses Cassandra in the backend, things like that. We don't do MapReduce in one language. We actually use Python, Java, Pig, and Hive. Although Hive is not really used, as I said, in our processing part of our pipeline. And I just wanted to share with you guys a bit, like, why do we use certain things. Spotify is a big Python house. We have when Spotify started, we hired a lot of Python developers. They started writing a lot of backend stuff. Our client is actually written in C++ or in Objective-C, depending on the platform. But a lot of our backend services are and were and are still written in Python. When we started running Hadoop, it started off with a small cluster. It's like, hey, how is this going? And the easiest way was to start with Hadoop streaming, using Python scripts to do so. The pros are that it's very fast to develop. You can really quickly prototype a job. And we have a lot of Spotify libraries that are available. So we have a lot of shared code that we can use. How to deal with log lines, how to deal with specific users. There's a lot of business logic in Python that we sometimes have to emulate when it comes to MapReduce. Some cons, obviously, are it's slower than Java. With MapReduce streaming, you have to step out of the JVM. You just get standard input, standard output. You can't have access to, you don't have access to real cool Hadoop APIs. Interacting with HDFS from your job is hard. And yeah, you get the overhead of the fact that it's outside of the JVM. Next to that, you don't get optimizations that some higher level languages like Pig, for example, and Hive give you. But similar, the optimization part is similar for Java. You don't have to optimize by yourself. But sometimes we do use Java where we really have to, because it's fast. It's, as I said, it's faster than Python. We get, for the jobs that we run, we see about 20% increase when we use Java. And you have access to Hadoop APIs. But yeah, it's a very verbose language. Deployment is sometimes hard. You have to build your jar, you have to upload it, you have to integrate it with the whole process, which sometimes can be tricky. And we don't have that many Spotify libraries available in Java yet, which is also sort of problematic because if we have a library, then we would need to maintain a Java version and a Python. So Java is used when we have to do some tricky stuff. Next to that, we use Pig. It's the pro of Pig. One of the pros is that it's very condensed. You can write very, very small scripts in very short time. So you don't have to have a lot of boilerplate code. I don't know how many of you have written joins in joining two data sets in MapReduce. You still have to have a lot of code to do that. In Pig, it's just join A with B, and you're basically done. So it's very condensed, and yeah, you get short iterations on the stuff that you develop. We're trying to push Pig more and more. Developers currently still sort of grab towards Python because that's what they know, they understand the language. We try to push more the use of Pig more. We actually hired one of the guys from the Pig Apache Pig project. He's a PMC in Apache Pig, so he's really out there trying to evangelize Pig, which I'm a big protector of Pig. Cons obviously is that developers who are not really aware of how MapReduce works or are not really interested in the data side of things, but they will have to use and learn yet another language amongst all of them. And the same goes for Java. There are not a lot of libraries available. So yeah, we have to sort of try to balance that. The last one is Hive. As I just said, hopefully many of you know Hive is a SQL-like language that generates MapReduce tasks and sends them off to Hadoop. It's great, especially for non-programmers. A lot of our analysts, we hire analysts that have SQL knowledge. They should at least be able to write SQL code or SQL queries. And for them, Hive is fantastic. They know how it works. They understand the relational database models. How do you join things? How do you do subqueries and things like that? They don't have to learn, or don't have to learn the whole MapReduce paradigm. It's sort of mind twisting if you start with it, then you have never encountered. But a con is that for using it in a pipeline processes, is that it has a lot of moving parts. You have a meta store, probably a Hive server that you use, and those can go down. And at the scale that we are at, those things will go down. So we try to avoid things, and we try to come up with clever things. some more technical details. So we use Java, Pig, Hive, and Python for writing MapReduce 1.0. We still use MapReduce 1.0. We're not on Yarn yet. Basically simply because we haven't taken the time to do it. And it doesn't add a lot of value at this point. In the future, definitely. Next to that, we use Apache Kafka for log collection. This is a system that was developed by LinkedIn for ingesting logs into HDFS, and it seemed to actually fit our use case pretty well. We're actually in the process of migrating to Kafka. We had a batch so we had a batch transfer system. So from our backend services, every hour all the data would be copied to some local storage, and from there we push it into HDFS. But we want more real-time data also in HDFS, and we want more guaranteed delivery, and that's Kafka provides parts of that, and what it didn't provide, we built ourselves on top of it. For big table stuff, we use Cassandra. We don't use HBase, which might be surprising given the fact that we have a very large Hadoop cluster, but that's mainly for historical reasons. We use Cassandra not only for analysis and for big data stuff, but we also use Cassandra in our online services. Our playlist system, for example, is a huge Cassandra cluster. We have invested a lot of time, money, and resources into Cassandra. We have a lot of Cassandra experts running around at Spotify, so we figured, okay, all the analytical stuff we can just as well do in Cassandra, so we don't have to care about HBase. We actually ran HBase for a while, 2 years ago, but HBase at that point wasn't very stable, so it went down all the time, caused more problems than it actually solved. So we ditched it and moved everything to Cassandra. For our relational database, we use Postgres, as I already said. To import data from Postgres and to export data towards Postgres, we use Scoop, a pretty cool tool where you actually run MapReduce tasks to import and export data in and out of your cluster. Before Scoop even existed, we used to dump data onto a machine, so one server, and then upload it to HDFS, but that had horrible performance, and also when that machine goes down, yeah, you're pretty much in the dark. So Scoop is great because it parallelizes using macros and reducers and all that kind of stuff. Just send a task to your Hadoop cluster and things will be done. And the last thing is we use Avro as our storage format. It gives us a schema with our data. And since we have so much data and there's so much types of data, we really need to know what schemas are. We can't constantly toy around with parsing stuff in different ways. So we like standardize on Avro. As I showed in the infrastructure overview, is we have we use Luigi. Luigi is an open source scheduler that we've written and open sourced it a couple months ago. Why did we do that? There aren't so many schedulers out there in Hadoop land. You have Uzi and Azkaban, and that's about it. And both of them didn't really fit how we want to use the scheduler. Uzi was way too XML-y, so there are lots of XML configuration that you have to do before you can actually write a job. Very Java-centric. Azkaban is a bit more user-friendly, but also still very Java, but Scala-centric. And we run most of our stuff in Python, so we would like to have better integration with Python. So we wrote Luigi, and you can find it on our GitHub page. As I said, it's written in Python, and we started building it as a scheduler for Hadoop jobs, but it evolved into sort of a generic scheduler. You can schedule whatever you want. You can talk to databases with it, you can talk to Hadoop with it, but whatever task you want to run at any given point, you can schedule it through Luigi. Luigi takes care of dependencies between jobs. That's, I guess, the biggest power, where if you have a job that produces some data and you have another job that depends on the first job, then yeah, you don't want that second job to start before the first data is in. So that's why we have Luigi. I would say check it out because I honestly really like it and I didn't even develop it. So looking at some history, how did we scale Hadoop at Spotify? We started with a very, very small cluster, probably, and that was before my time, so I don't have the whole grandfather story of that, but we started with a very small cluster, initially probably run on people's desktops and just testing it out, but then we sort of scrapped together some older servers that were sort of half decommissioned, and that grew to a cluster of 37 servers, but the problem was that they were very imbalanced. We had machines with 7 terabytes of storage, we had machines with 20 terabytes of storage, and that caused a lot of issues, and yeah, the hardware was older, things went down and stuff like that. For a while we tried out, after that we tried out Elastic MapReduce, so we moved all our data to Amazon, which was great. Amazon is great. I don't know how many of you guys use Amazon for doing MapReduce. Not so many, I'm surprised. I think it's a great way to, especially to start off with Hadoop. Run a bunch of jobs in EMR, you just pay by the minute. Amazon is cheap, in between quotes, up until the point where you actually do a lot with it and you store a lot of data, then it all of a sudden becomes really, really expensive. Or at least what we did became really expensive. So I remember one of my colleagues, manager, who was responsible for that, basically for the money. He came running out of a meeting, screaming like, "This is not going to hold up, guys. We really need to do something." So we analyzed, okay, what does it cost to build an in-house server or in-house cluster? And we figured out, okay, within a couple of months we can actually we can earn back the amount of money that we currently spend on Amazon. So we started off with a 16-node cluster. Put that in. We have multiple different data centers, which poses somewhat of a problem when it comes to data, actually. But we have 4 different data centers around the world, 2 in Europe and 2 in the US. And we built our Hadoop cluster in London. But that means that all the data or the data from the US has to travel across Atlantic. And that's slightly problematic because bandwidth is limited across the big pond, and also it's costly and it's slightly slow. So we try to come up with clever tricks to move that data. We do have the vision that we keep our cluster in one place. You can have a strategy where you put a Hadoop cluster in each different site, but we do a lot with global aggregates. And music listening behavior is kind of global. There's a local aspect to it. You guys all here in Poland listen to Polish music. I don't think that a lot of people in Argentina, for example, would listen to Polish music, but a lot of music is actually global. So we want to do a lot with that global data, so we want to keep our data in one place. Anyway, so since we started with 60 nodes, we've done extensive capacity planning. How much data do we use? How much data do we produce every day? How much do we ingest? What's the usage on our cluster? And try to order new batches of servers every 6 months. And we've done that up until a couple weeks ago, where we were at 190, and as I said, we just put the order out for 500 more. And we really see an exponential growth in both the usage of the volume of data that we have, and also the amount of users that use our system. And that means that we really need to think about data retention. What data do we keep, and what data do we ditch or do we archive and don't have in our Hadoop cluster? Hadoop is nice because it gives you replication for free. And so some people might think, Hadoop is just write once to it and at least you have 3 or 4 or 5 copies of your data. But at this scale it becomes pretty costly as a backup solution. There are way cheaper backup systems out there. So we're really working on data retention to do so. So our couple lessons learned. 4+ years of Hadoop has taught us a couple things. Hadoop has brought us very, very far. If you look at Spotify, a couple of years, as I said, a couple of years ago, decisions were based on a gut feeling. Now people are far more data driven. So they come up with all sorts of questions for their product, but also ask the question, do we have data for that? Can we test hypotheses that we have when it comes to features? So we try to provide Hadoop as more of a platform to our users, internal users that is. So for developers who work with features, for managers or product owners to do analysis on their features, to management to provide those dashboards and things like that. Another lesson that we learned is that commodity hardware doesn't really mean it's cheap hardware. As I just said, you can't just take your old 486 stack and run Hadoop on it. You really need some beefy machines. It's not as expensive as some really big enterprise solutions, but you still need decent Dell or HP or IBM servers, but at least you don't need sort of the exotic stuff. Also, Hadoop is not a silver bullet. It doesn't replace your SQL stuff. It doesn't replace things, other analytical systems. It's really an addition to what we do, at least. Hadoop is also, it's a very complex system. It needs love. It's not that you put Hadoop in a corner, you're racked with Hadoop servers, and then like, oh, just dump data on there and everything will be fine. It needs a lot of love. It will go down, things will break, you will constantly have to optimize. There are so many knobs to turn and buttons to tweak in Hadoop. Luckily, we do have Adam working for us who's really crazy about that stuff, so he goes and tweaks all the knobs to fit them to our workload. And our workload is probably completely different than at Facebook, at Twitter, at LinkedIn, Netflix, other big Hadoop users. So again, needs love and attention. But it's very lovable, I think. The yellow elephant is pretty cute. And if you really want to sort of get the last bit out of your can, I don't even know if that's an English expression. You will have to extend Hadoop. So we use our own way of storing data, our own data format that works for us. So we have extended parts of Hadoop, input formats, output formats to adjust to that situation. If you use Hive or Pig, you will probably have to write your own user-defined functions that fit your own business logic. And again, so it's not just like, we put Hadoop there and everything will be heaven and managers will be happy with data and things like that. You really have to invest in it as a company. But nevertheless, Hadoop is a lot of fun. I'm myself pretty passionate about this stuff. I luckily work with colleagues. My team is currently about 12 people, and they're all really, really passionate about Hadoop. And the bigger the better. I actually remember when I was interviewing Adam at Spotify, his first question was, how many nodes do you have? How much data do you have? And it's a question that I hear quite often. Because people that I work with, they just want more and more, and they get really happy when we say, we just ordered 500 more servers. And myself as well, I love that kind of stuff. So are there any questions?
Yeah, quite interesting examples at the beginning. Did you actually use any of those conclusions
It's a good question. In this case, I'm not completely sure, but where you could use it for is, for example, advertising targeting. So we have an ad product, and you could think like, okay, this may be a silly example, but I think it's quite close to the truth. If you see that after parties, then at that moment you could actually play ads for the local kebab shop. Stuff like that. You can do better ad targeting so that people start buying products. So it's very interesting to see how can you target people, for example.
I have two other questions.
Yeah, sure. Go ahead.
Would you say that Hadoop is a kind of base for your data warehouse, or is an additional backup or a kind of back office for the data warehouse?
No, we use Hadoop mainly as our data warehouse. So most of our data goes into Hadoop, is directly accessible through, and people that do the data warehouse stuff, they mostly use Hive to do so. But there are other people building, even on Hadoop, building OLAP cubes, OLAP-like cubes to do their analysis on. We don't have an additional system, at least, where we put things. We do put a lot of aggregates into SQL, but yeah, then it's hard to do like all that kind of stuff. You often want to really dig down and drill down into your data. I'm honestly really excited about Impala, for example, that Cloudera released last week. I think it went gold. So that allows us to even do faster big data query stuff. So we'll be definitely looking at that.
And the last thing you said about moving from 1 hour dumps from logs to some faster stuff. Do you targeting to go with the Hadoop for real time or near real time?
Well, with Hadoop, it's still a little hard because what we see, for example, we use Kafka, and Kafka is near real time. We have a latency, I think, of about 4 seconds from when somebody plays or an action happens in our client until it ends up in Hadoop. But the thing with Hadoop is that as soon as you don't close a file in Hadoop, it's not really accessible. So you don't get file sizes and things like that. You could sort of read it, but it's not optimal. You don't want to start processing the file when it's not closed yet. And the thing in Hadoop, you want big files. So small files, Alan will come to that later, but small files will basically kill your Hadoop cluster. So in that way, it's not, we can't use Hadoop yet for close to real time. There are some interesting developments going on with Yarn, where you can actually run Storm, for example, in Yarn, and then use HDF as data, and that's a very interesting thing. We do have a Storm cluster at Spotify, but it's not in production. It's more of sort of a test base. And the interesting thing was that about half a year ago, more than half a year ago, people started talking about, oh, real-time analytics, that's the thing. We really have to have real-time analytics. So we started, okay, let's just try this out. Let's do Storm. Let's try to come up with some stuff, put data into Cassandra. But we figured, like, the things that we do, we don't really need that low latency. And like doing real good analysis, you often need more data anyway. So statistical significance is hard to reach when you have 1 minute of data. We tried it out for example, A/B testing, where a feature was deployed in 2 versions, and then we could very quickly see how different they were performing. But to do a really good A/B test, it has to run for a week or 2 weeks anyway, because you have seasonal influences and things like that.
So what was the reason for moving to Kafka?
Kafka gives us, it does give us that low latency, but we don't particularly need it in Hadoop. But with our current system, we had a latency from when an action happened to when it was completely available for others in Hadoop for 4 hours, and that was a bit too long. So we tried to cut that down. And also, Kafka gives us the ability to hook in Storm, for example. So we don't have to have multiple paths of our data to provide data to Hadoop and to provide data into Storm. So we have Kafka as sort of our centralized data collection system, and one output is Hadoop, and another output is Storm. And there could be all sorts of other outputs, like services that really want data in our, not real time because it's not sub-second latency, but at least less than 10-second data they can use with Kafka as well. So it's a bit of a win-win for us going to the system.
Thanks.
One question: do you use Hadoop to improve search results in the Spotify? Are they personalized, or is it one big, I don't know, search engine that searches everything?
Hadoop is, the interesting thing is that the team that, and maybe I didn't explain that at all or good enough, the team that I'm working on, we sort of try to create a data platform where other teams can do whatever they want with data. So, me and my team, we don't really care how others use it, and it's interesting because I have a hard time answering your question because I don't know what they do. The same goes for radio. Those guys, they run their jobs and they're quite heavy users of our Hadoop cluster. And I just see the output like, okay, we have a pretty awesome radio feature. But how they do it, no idea. So it could well be that people actually use Hadoop for search optimization. It could also be not, but that really depends on company priority.
You said about this problem of the bandwidth of transferring data between US and Europe.
Yeah.
And I didn't catch what was the solution. Did you already solve it somehow? Or?
Well, we try to optimize our bandwidth usage, try compression, try to send data in a more efficient way. Batching data often works, like sending larger batches of data over the Atlantic works better than when you do message by message, for example, or the other way around. I'm not a big expert on how networks work in that sense, but we try to do our best, but it's still a hard problem. We haven't completely solved it. And it's also like when those links, they go down, and they go down more often than if you have like two data centers next to each other. Routing problems on those transatlantic connections, things like that. So you have to catch up data that is generated. And those are problems that we haven't completely solved yet. I think we're on a good track of doing so, but these are very, very complex things to do.
And the second question, taking on, does it come more from ads or more from users paying? Because I'm thinking, does it pay off to make some complex analysis on ads? Because if there is not, if it's the biggest source of income, then it does pay off. And otherwise, I think it could something.
You would have to ask our financial guy. I'm not too familiar, or I can't expose one of both. How much money we make on different parts of Spotify. But, yeah, that's more up to the business too. But we've seen that Spotify is a very viable business model where we have a free tier and we have a paid subscription tier. Any more questions? Right, then I have one more small thing that I wanted to present to you guys. What is the biggest annoyance when running this command?
No interactive mode.
No interactive mode, okay? Anything else?
Tab is not working.
Huh?
Tab is not working.
No tab completion. Okay, yeah, that's a good one. I'll come back to that. I forgot about that, but I didn't forget about it, you'll see. Anything else? For me,
You have to start a virtual machine.
there you go. That was my biggest problem. It's slow. It's really slow. It takes a couple seconds to start that command before the client actually starts communicating to the data. So you have a JVM startup time. It takes a couple seconds.
It might even not finish. Like,
Yeah.
an hour cluster.
Thank you, Anna. It will always finish. Don't listen to him. On our cluster. Okay. It should finish. Anyway, so JVM has quite a bit of overhead. It takes a couple seconds to. JVM starts in like a second or so. It loads in a whole ton of jar files, Hadoop stuff, logging stuff, all sorts of things that are pulled into Hadoop projects. Yeah, stuff you really don't need for just listing files. And that's quite problematic for us because, as I said before, we use Luigi to schedule. And what the Luigi scheduler does is when you want to see if one job is finished before you can run the next, you want to actually, we check on HDFS, is the output there? How does the output sometimes look? Do we have enough files? Things like that. And if you do that once or twice, that's fine. But we run thousands of jobs, and Adam probably has the real number of how many jobs we run
Per day?
per day.
Around 10,000.
10,000 jobs. So all those 10,000 jobs do check multiple times on HDFS. And since Luigi is written in Python, it's pretty hard to constantly step out into, or to actually spawn the Java or Hadoop command, read the output, takes a couple seconds, things like that. We also have, within WHUG, you can say, okay, I want to have at least X amount of days of data before I actually start doing something. So if you want to have a year of data, we'll go 365 days back, just to check, which is 365 about 3-4 seconds, and that's quite an overhead when it comes to this scale. I personally was really annoyed with that, so I created what I call Snakebite. We've open sourced it under Spotify flag, and it's a pure Python HDFS client. Luckily, Hadoop guys upstream, they moved from Java serialized objects to using protocol buffers to talk from client to name node, and also from name node to data node, and all the components within the Hadoop ecosystem. So I figured, you know, if it talks protobuf, why not do that from Python? So created a client library and a command line tool that does only use protobuf. It just does, creates a network connection, does some RPC magic, and sends protocol buffers. And it's far, far faster than Hadoop command line. So how much faster is it? This was a very small test. I ran Hadoop FSLS 10 times, and I did the same with Snakebite. Snakebite finished in 1.6 seconds, so that's 10 iterations, and Hadoop did it in 14. I actually wanted to run it, I started off with doing it 1,000 times, but I didn't want to wait for the top one. That one, I'll still get 1,600 seconds, that's what order, I think. But it's much faster, and especially if you use it as a library in your Python code, then it's very, very, very quick, because you don't have the overhead even of starting with. So this is, I open sourced this last week, and you're basically the first guys that I talk in real life about it. So you guys are preview. And you're ahead of Krakow, where we will be tomorrow. I don't know how is the relationship between Krakow and there's competition there, soccer and things. Good. So you guys have the preview. Yeah. So this is sort of my end of my presentation. I'm doing a shameless plug here. We are hiring. So if you are interested in working at Spotify, doing some cool Hadoop stuff, working with one of the largest clusters in Europe, please come talk to either me or Adam after the meetup. Also, I'm not Swedish. I didn't tell anybody of you, but I'm not Swedish. I'm Dutch. So I moved to Stockholm. Adam moved to Stockholm, so we can tell you a lot about how cool that city is and what it means to move. So just come and talk to us. If you have any other questions, just email me. It's my first name at spotify.com or find me on Twitter. Thank you.
Nazywam się Adam, ja pracuję jako data engineer w Spotify razem w zespole Woutera. I tutaj dzisiaj podczas tej prezentacji chciałbym Was zabrać na taką podróż, w której chciałbym opowiedzieć o najbardziej interesujących i ekscytujących rzeczach, które zobaczyłem po dołączeniu do Spotify. Więc ja w przyszłości pracowałem z kilkoma testami w Warszawie i to było naprawdę fajne, dużo rzeczy mogłem się dowiedzieć. Wiedziałem, co tam w trawie piszczy, ale trochę czułem się jak w lesie. Ale w momencie, kiedy dołączyłem do Spotify, zobaczyłem dużo rzeczy i tak poczułem, że jestem w tej prawdziwej dżungli, gdzie wszystkie te zwariowane, dzikie zwierzęta, łącznie z żółtym słoniem, biegają, robią dużo szumu i o tym chciałbym dzisiaj powiedzieć. To, co mi się bardzo podoba w Hadoopie, to jest to, że on jest związany z najróżniejszymi technologiami. I u nas w zespole pracuje kilka osób i właściwie to jest naprawdę fajne, że każdy z nas może znaleźć coś dla siebie. I ja na przykład pisanie Pythonowego kodu nie generuje u mnie takiej dużej ekscytacji, więc na przykład ja wolę zajmować się bardziej rzeczami związanymi z administracją Hadoopa, utrzymywaniem jego, zmienianiem ustawień. Niektórzy koledzy wolą więcej dewelopować, udzielać się w społeczności open source i to jest bardzo fajne, więc oni mogą robić to, ja mogę robić trochę co innego. No i fajne jest to, że faktycznie jest to robić, bo Hadoop jest skomplikowanym, złożonym systemem, on jest ciągle rozwijany, cały czas pojawiają się nowe funkcjonalności, cały czas na przykład pojawiają się nowe rekomendacje, jak coś ustawić, one zawsze i tak kończą się słowami uruchom swoje benchmarki, bo nie wiadomo jak to się zachowa. Na jednym przykładzie zespołowym działa to inaczej niż na drugim. Więc to jest całkiem fajne. I oczywiście te najlepsze praktyki są właśnie w tej chwili ustanawiane, bo coraz więcej Hadoop staje się coraz bardziej powszechny. Też zmienia się hardware. Na przykład Hadoop został wymyślony w momencie, kiedy taka typowa maszyna miała 4-8 GB RAM. No teraz już takie typowe to mają 30, 48, 64, więc dużo rzeczy się zmienia. Więc zacznijmy. No i ja tutaj będę opowiadał o tych ciekawych historiach, które zaobserwowałem. Pierwszą z nich była sytuacja, kiedy pojawił się ticket o tym, że dany użytkownik nie może uruchomić zapytań w Hive'ie. I to zapytanie jest poprawnie syntaktycznie, kompiluje się, działa super na małych ilościach danych, ale failuje na dużych. Co ciekawe, jeżeli ten użytkownik da to zapytanie swojemu koledze, ono zadziała. I to, co jeszcze wiedzieliśmy o nim, to że jest trochę złożona obliczeniowa i użytkownik ma poprawne uprawnienia do HDFS-a, do Hive'a, także to wiedzieliśmy. I w momencie, kiedy ten użytkownik uruchamiał to zapytanie, widzieliśmy, że na klastrze pojawiają się problemy. Name zaczyna być unresponsive i przez ten czas on zatrzymuje się na jakiś dłuższy okres czasu, traci połączenie z datanodami, datanody padają, tak naprawdę pada ich 10, 20, czasem 40, więc naprawdę poważna sprawa. I zaczęliśmy się zastanawiać, o co tam działa. I po jakimś takim większym debugowaniu znaleźliśmy takie komunikaty w blogach Name'node'a. I on rzucał bardzo wiele warningów i wyjątków. I pojawiało się coś takiego, że nie ma takiego użytkownika na HDFS, nie rozpoznaje go, a właściwie nie rozpoznaje grupy, do której on należy. I jak się tak przyjrzy Hadoopowi, no to biorąc pod uwagę takie jego domyślne ustawienia, no to on jest bardzo ufnym zwierzę i jakby nazwa użytkownika jest wzięta z klienckiej maszyny, nie jest weryfikowana wcale, a grupa, do której ten użytkownik należy, jest identyfikowana przez maszynę, na której działa Name przy użyciu Linuxowego polecenia. I w momencie, kiedy ten użytkownik nie ma konta na tej maszynie, pojawiają się takie wyjątki. Więc to, co może rozwiązać ten problem, no to rozwiązanie jest proste. Po prostu trzeba zapewnić, że każdy użytkownik, który ma dostęp do klastra, musi być w stanie być zidentyfikowany przez Name'node'a. No i taki najprostszy i dosyć quick and dirty sposób to jest tworzenie tych kont ręcznie. Ewentualnie można użyć do tego Active Directory albo LDAP-a po to, żeby Name'node wyszukiwał informacje o użytkownikach w jakiejś tam globalnej, będzie tam jak LDAP. Ewentualnie można użyć Kerberosa. My zaczęliśmy od tego pierwszego sposobu oczywiście, bo był najszybszy. Od razu panika, 40 węzłów pada, nie wiadomo co robić. W końcu to zidentyfikowaliśmy i naprawiliśmy. Więc to było coś całkiem fajnego.
Przepraszam, mam pytanie. A tu było napisane, że zapytanie działało dla małych danych.
Tak, dlatego że te wyjątki pojawiały się i warningi tylko przez chwilę. W momencie, kiedy było duże obliczenie, bardzo dużo tasków zostało stworzonych, one wszystkie odpytywały o coś nameloada i przez dłuższy czas, jak to trwało, to nameload tracił komunikację z niektórymi węzłami. Jeżeli to trwało dłużej niż 10 minut, no to te węzły były w momencie, kiedy nameload się obudził, były uznawane za martwe. Więc...
A te wyjątki leciało na nameloadzie, tak?
Słucham?
To na nameloadzie leciało, te wyjątki.
Tak. I to powodowało, że ten proces był mniej aktywny. Ok. W przypadku Hadoopa wszystko praktycznie ulega awarii, procesy failują, dyski padają, komunikaty nie dochodzą, demony nie chcą startować. No i to jest taki generyczny problem, mamy dużo jakichś takich tiketów, coś tam nie chce wystartować. No i jeżeli chodzi o data noda, zwykle to jest związane z jakiegoś typu awarią dysku. Kiedy pierwszy raz to zobaczyłem, byłem dosyć podekscytowany, że nawet w środku nocy wysłałem maila do wszystkich. Po jakimś czasie to stał się chleb powszedni. No ale na szczęście awaria awarii nie jest równa, więc zawsze jak się ktoś loguje na jakieś takiego, żeby zdebugować tego nameloada, może zobaczyć różne wyjątki, więc to też jest związane z jakąś awarią dysku, kiedy dysk ulega awarii i maszyna restartuje się i ten dysk zostaje zamontowany tylko w trybie do odczytu i na przykład nie można usunąć plików, które blokuje do danego katalogu. Tutaj nie wspominałem, ale jest takie ustawienie, które domyślnie, jeżeli mamy ileś tam dysków na węźle, jeżeli jeden z nich pada, to wtedy proces data node również pada. Możemy zwiększyć tą wartość, awarię większej ilości dysków, dzięki czemu na przykład jak u nas my mamy 12-węzłowe dyski, możemy zwiększyć tą liczbę do na przykład 2-3 i wtedy jesteśmy bardziej odporni na awarię. Bo taka awaria to co powoduje, no to od razu pliki są replikowane, dużo transferów między węzłami, my przeciętnie teraz trochę dużo miejsca używamy na klasie, mamy 20 terabajtów, prawie że 20 terabajtów na węzeł zajęte, więc jak nam węzeł pada, od razu 20 terabajtów jest kopiowane po sieci. No i tak jak Wouter powiedział, rozbudowujemy naszą infrastrukturę, dokupujemy 500 kolejnych węzłów, więc wtedy będziemy mieli ponad 8000 dysków i one zaczną ulegać awarii. Przeciętny okres takiego dla dysku, średni czas pomiędzy awariami to jest od 3 do 5 lat, więc jak teraz nam jeszcze mamy dużo nowych dysków, bo sporo węzłów kupiliśmy w zeszłym roku, więc one jeszcze tak często nie ulegają awarii, ale za 2-3 lata no to będzie tego naprawdę sporo. I już teraz widzimy, że na przykład część dysków jest wolniejsza. Część tych najstarszych dysków jest wolniejsza od tych najnowszych, o 30%. Według benchmarków, które zrobiłem. Więc jak teraz dodamy super nowe, kolejne węzły, to te różnice jeszcze się powiększą i może wtedy kolejne rzeczy będzie trzeba konfigurować jak raz.
Mam pytanie, używacie takich normalnych dysków, czy jakieś SSD?
Normalne. Wydaje mi się, że normalne.
Tam pisałeś o spekulacjach, w ogóle nie ma się możliwe.
W tej chwili wyłączyliśmy to, ponieważ to jest fajnym featurem, jeżeli na klastrze bardzo często widzi się jakieś problemy z hardwarem, z połączeniem sieciowym, z jakimś obciążeniem, na przykład część węzłów jest kompletnie stara, część super nowa i ten feature polega na tym, że jeżeli jakieś zadanie wykonuje się relatywnie wolno, dużo wolniej, no to dodatkowa kopia redundantna jest startowana na klastrze i ta, która wykona swoje obliczenie pierwsze, wyniki od tej są wzięte i druga jest zabijana. Więc w naszym przypadku my mamy klaster, który ma taką samą konfigurację na każdym węźle. W tej chwili my tak nie mamy zbyt dużo problemów, nie widzimy zbyt dużo różnic oprócz tych 30% na dyskach. Więc tak nie ma specjalnej potrzeby, żeby to uruchamiać, bo według takich obserwacji, które mamy, ta redundantna kopia, która gdzieś tam się uruchomi na klastrze, ona i tak się wykonuje mniej więcej z tą samą prędkością co oryginalna. Więc no i to jakby powoduje, że może ten speculative execution może pomóc jakiemuś jobowi, żeby wykonać się szybciej, ale na przykład przez to dodatkowe sloty są zużywane, które mogą spowolnić inne joby. Więc z jednej strony pomagamy komuś, innym odbieramy. Dodatkowo, jeżeli na przykład redundantnie wykonywane jest zadanie typu reduce, to ono musi znowu też po sieci pobrać wszystkie wyniki od maperów, wykonać się i na koniec jeszcze zapisać dane do HDFS-a z replikacją 3, więc no to jest sporo narzutu i my to wyłączyliśmy. Na szczęście teraz pojawiły się takie nowe, fajne ustawienia w Speculative Execution, że można je włączyć globalnie, ale ustawić limit, ile na przykład takich tasków może się redundantnie wykonywać. Więc to jest fajne, bo można przeznaczyć na przykład 10% zasobów taska na to wykorzystanie. To są nowe ustawienia, które gdzieś tam wyczytałem 2 tygodnie temu o nich, jeśli ich nie spróbowaliśmy w praktyce.
No właśnie, że produkujecie są takie same jak odpowiedzi? To właśnie dobry interes wpłynie na ten czas.
No teraz te co kupujemy to będą trochę lepsze. Nie jestem pewien, czy one będą miały 54 GB pamięci. Prawdopodobnie dopłynę pamięć do poprzednich, ale wydaje mi się, że te serwery, modele tych serwerów będą inne.
Wydaje się, że tego są ograniczność zachować w miarę.
Tak, ale jak się spojrzy na te wszystkie klasy budowane przez duże firmy, to one tak rosną organicznie. Dodawane są coraz nowsze węzły i widać to, że część węzłów jest starszych, ma trochę inne konfiguracje, no i one wciąż są używane. Ja na przykład chwilę rozmawiałem z jedną osobą z LinkedIna i oni na przykład używają Speculative Execution włączone w tym momencie, bo widzą, że ta różnica przy prędkości czytania po dysku jest istotna. To jeszcze oczywiście zależy od tego, kto jakie zadania wykonuje, bo jak wykonywane są jakieś grafowe obliczenia czy machine learning, no to wtedy ten czas czytania po dysku jest trochę mniej ważniejszy niż później długie minuty przetwarzania czegoś. Więc to trochę słaba odpowiedź, no ale trzeba jakieś tam benchmarki uruchomić. No, kolejny problem, który gdzieś tam się pojawił, no to jest to, że zadania były ubijane, kilowały z jakiegoś powodu, nie wiadomo dlaczego. Tutaj mamy przykład jakiegoś joba, który się wykonywał, on się wykonywał długie godziny, ponad 12,5. Wciąż się nie wykonał. Tylko jeden task failował, ale za te tysiące z nich było zabijanych. No i pytanie właśnie dlaczego? Jak patrzyliśmy na logi, mniej więcej to tak wyglądało, że task był zabity przez użytkownika. Ktokolwiek był tym użytkownikiem. No i zaczęliśmy obserwować to i się okazało, że znowu tutaj jest problem z długimi zapytaniami, które wykonują się godzinami, zużywają dużo zasobów klaska. Oczywiście te zadania nie były zabijane przez job trackera z okazji tego feature'a Speculative Execution, ponieważ nie można dołączyć tego. Jak patrzyliśmy w logi, to okazywało się, że job tracker dostaje wiadomość o to, żeby ubić danego taska, ale w momencie, kiedy patrzyliśmy, kiedy one były ubijane, jak się spojrzy tutaj, kliknie dalej, to można zobaczyć po jakim czasie uruchomienia tego zadania, tak, task został zabity. No i zauważyliśmy, że one bardzo szybko po starcie są zabijane, a jeżeli nie są zabijane, no to już uruchamiają się długie godziny. No i to były zadania hive'owe, które się wykonywały w swojej specjalnej puli. Z przyczyn praktycznych, żeby było łatwiej zarządzać takim dodatkowym systemem, który mamy, wszystkie takie ad hocowe zapytania hive'a są wykonywane jako jeden użytkownik i są zorganizowane do jednej puli zadań hive'owych. No i właśnie, kto może wysłać takie zapytanie, żeby zabić danego taska? Może to zrobić użytkownik, ta wiadomość, ten message śmieje nam sugerować. Może to zrobić job tracker, właśnie jeżeli jest speculative execution włączona, albo w momencie, kiedy cały job failuje, to wszystkie taski, które należą do tego joba, są też ubijane. No i okazuje się, że może to zrobić także w schedule. No i była to prawda, bo fast schedule stara się być sprawiedliwy. I żeby to zrobić, on sobie zabija. I zabija te taski, które należą wykonują się zbyt długo, niż przewiduje sprawiedliwość w jego mniemaniu i stara się zabić tym jobom, które potrzebują sloty, stara się przekazać sloty z jobów, które wykonują się zbyt długo. Więc okazywało się, że pula hive'owa wykonywała zbyt dużo zadań. Pozostałe pule potrzebowały ich, żeby spełnić swoje wymagania SLA i fast schedule ubijał hive'owe taski od czasu do czasu. I to było związane głównie fast schedule ma dwie heurystyki zabijania tasków. Jeden polega na tym, że specyfikujemy minimalną ilość slotów, które dana pula potrzebuje i timeout, po którym sloty z innych pól mają być przekazywane w momencie, kiedy ta pula ich nie otrzymuje. No i w naszym przypadku chodziło właśnie o to, że niektóre pule nie miały zagwarantowanego minimalnego udziału w klastrze. To, co my zrobiliśmy, to tak naprawdę ustawiliśmy limity, ile maksymalnie zadań typu ma się wykonywać w puli hive'owej. No i to rozwiązało nasz problem, ale jest jeszcze kilka innych rozwiązań, które w mniejszym lub większym stopniu rozważaliśmy. Można byłoby na przykład wyłączyć tą właściwość, która nakazuje ubijać te zadania, ale no, byłoby to po części dobre rozwiązanie, ale to by wciąż nie zapobiegło przed taką sytuacją, że klaster jest zdominowany przez hive'owe joby uruchomione na klastrze, które wykonują duże obliczenia. Po prostu one by się dalej wykonywały, a nie byłoby tego zabijania. Nie wiem, czy to jest prawda, ale ja mam wrażenie, że na przykład capacity scheduler mógłby być trochę lepszy, bo on właśnie on ma takie podział klastra na kolejki, które są bardziej takie sztywne i to jest tak jakby dzielenie klastra na podklastry. Oczywiście każda taka kolejka może być elastyczna, może wykonywać więcej zadań, jeżeli inne kolejki są puste, ale nie ma zabijania jobów i na przykład według kolegów im się to sprawdza. Inny fajny problem? Job tracker zaczyna się być bardzo wolny, mimo że kiedyś był bardzo szybki i ludzie zaczynają wysyłać dużo maili, są zażenowani, że trzeba czekać bardzo długo. No bo to jest duży problem. U nas wiele osób jest uzależnionych od danych, od wykonywania obliczeń. W momencie, kiedy są jakieś klaster daje nam w kość, to dużo ludzi nie wie, co z sobą robić, chodzi, kręci się, wysyła maile. Gdziekolwiek byśmy nie byli, oni znajdą nas i będą się wypytywać, co się dzieje. No i znowu tutaj problem z dużymi zadaniami, znowu z Hive'em, bo w przypadku Hive'a jest bardzo łatwo napisać zapytanie, które naprawdę wykona się na tysiącach, zużyje dziesiątki tysięcy nawet slotów. Największą rzecz, którą jak widziałem na naszym klastrze, to task, który chciał służyć 120 tysięcy, wykonać 120 tysięcy zadań map. On się wykonywał 80 godzin i na koniec sfailował. Ale mam go w statystykach. Nawet wiem, kto był gotowy. No dobra. Jest też takie ustawienie konfiguracyjne, które pozwoli ustalić limit, jak dużo tasków może dane zadanie stworzyć, żeby się wykonywać. Jeżeli ten limit jest przekroczony, to job nie startuje. Więc stwierdziliśmy, że to jest super rzecz, żeby trochę ukrócić takie praktyki, żeby aż tak dużo takich dziwnych zadań, które przeliczają najpopularniejsze nasze zbiory danych z ostatnich kilku lat, że niekoniecznie one muszą się wykonywać, albo jeżeli już muszą się wykonywać, niech ktoś się zoptymalizuje, żeby na przykład dziesiątki tysięcy jednominutowych zadań typu map się wykonywało. Więc stwierdziliśmy, że to zmienimy, no ale padło pytanie, na co to zmienić? Czy 50 tysięcy będzie dobre, czy 30? Czy może jakiś kompromis, 40 tysięcy? No i to był rzeczywisty białek, który się pojawił u nas na filmie, zaczęliśmy to sobie dyskutować. No 40 brzmi całkiem nieźle, nie wiadomo dlaczego. No i właśnie kolejne pytanie, czy my powinniśmy takie...
Yeah, I know you anonymize those names, but I'm actually very curious who that were.
I was in this dialogue.
Okay.
I was fun. Why not Adam? Okay, it was me. One moment after, I asked this question to myself. Dlaczego? Czy powinniśmy zgadywać takie rzeczy, czy może skoro twierdzimy, że jesteśmy firmą w dużej mierze opartej na danych, to czemu tych danych także nie wykorzystywać do zmieniania ustawień Hadoopa? Przecież nie mamy. No i zrobiłem takie rozeznanie, co kto kiedy obliczył, ile to trwało. I się okazało, że największe, przeanalizowałem 500 000 zadań, które się wykonywało na naszym klastrze w ciągu ostatnich 2 miesięcy. Największe produkcyjne zadanie wykonywało 22 000 tasków, a wszystkie inne to były animokowe zapytania, które gdzieś ktoś tam kiedyś obliczył, wykonał, zostawił na weekend, później jak się okazuje, większość z nich one failowały i były killowane z jakiegoś powodu. Więc ustawiliśmy to na 23 000. I właśnie teraz czekam na maila, kiedy ten limit zostanie złamany, ale na szczęście już wiemy, co pisać. Nie działa. Na szczęście, to co zrobiliśmy, żeby przygotować odpowiedź,